Hi everyone, so this is the last section on the periodic motion section of the course, where we're going to look at what we call forced vibrations. So far throughout the simple harmonic motion topic, we've looked at the idea that we displace an object from its equilibrium position and then it oscillates due to a restoring force always acting it to return it to equilibrium. And that was essentially it, that it was left to its own devices is the key thing. What we're going to look at now is what happens when there are other forces also acting on the system, and there's two versions of this. There's damping forces, and then there's forces that actually will be applied to increase the motion that we'll be talking about in a second, called forced vibrations. So here's the reminder again, it's only simple harmonic motion when that restoring force we just mentioned is in the opposite direction but directly proportional to the displacement. So that was the natural systems that we've looked at so far. We displace them from equilibrium and they oscillate around that equilibrium position, constantly trying to return themselves to it, but essentially overshooting when they get there. So as we said, we've talked about free vibrations so far. We're not called it that to this point, but these are vibrations where there's no external forces acting to either remove energy from the system or add energy to the system. So once it's displaced to equilibrium, that's it. It's left alone. And that's called a free vibration. The frequency of that oscillation, as we've looked at in different circumstances, the spring mass and the pendulum system, that's determined by then the physical internal characteristics of the system, and therefore that's known as a natural frequency, which is sometimes designated the symbol F0, as you can see there. So the natural frequency is the frequency that it will oscillate at if you just leave it alone. Now we're going to introduce the concept of damping now. We've not looked at damping throughout the course yet. We've sort of mentioned it in passing a couple of times, and you might have considered how you'd compensate for damping perhaps in your required practical plans. But damping is the reduction in the amplitude over time due to some resistive forces acting on the system. So we're not looking at perfect systems, we're looking at systems that are subject to friction, air resistance, and forces that will remove energy from the system. And they transfer that to the surroundings in the same way that we've considered lots of energy transfers to the surroundings throughout the course, and you'll continue to do so. And it is the reason why actually if you let a pendulum swing for long enough, it will eventually come to rest at its equilibrium point. It will return to equilibrium eventually. It won't always overshoot as it loses a little bit of energy on each cycle. Now, there are a few different types of damping to look at, and actually we have to be quite careful about the terminology here, and if you look and do your own research, there's a few terms that are used interchangeably that really shouldn't be used interchangeably, and we need to be very careful with. So doing your own research, do be careful, because there's some incorrect essentially labelling and terminology widely out there on this, so do be careful. So we're going to first of all look at the idea of underdamping, which is the most sort of simple to understand. Basically what this means is that the amplitude of the oscillations will reduce gradually over time. So in the first cycle it will have go almost to its amplitude, then the second cycle a little bit less, and the third cycle a little bit less, so on, so on. It still oscillates with simple harmonic motion, but it's just that the amplitude is essentially reducing each time it goes through. So you can imagine this just with a pendulum or a spring mass system that slowly returns to its equilibrium position. It's called underdamping. We'll talk about some of the misconceptions in a little bit. And when you look at the amplitude of each cycle, then actually that is an exponential decay. We'll talk a lot more about exponentials throughout year 13 studies, but if you look at the lower graph here, you'll see that as the blue line, the actual position changes over time, the purple line maps the change in amplitude throughout that, and that is actually an exponential decay. Now with underdamping there is a little bit of confusion about the effects on the frequency. Essentially, damping of any type will affect the frequency of the system. If you're going to introduce a resistive force, that's going to increase the time period, slow down the oscillations a little bit, and therefore the frequency will slightly reduce. However, in most contexts with simple harmonic motion, if you're considering just, say, for example, our pendulum and our spring mass systems again, they undergo a large amount of oscillations before they'll reduce to rest under normal circumstances, and the damping won't be measurable between individual cycles easily. So actually, we can consider those to have a constant frequency and have the same natural frequency as if they were undamped, because the change is actually pretty much negligible. And the exam board for those sort of circumstances will expect you to consider them to be the same. But in reality, if that damping is a little bit heavier, then it will begin to notably reduce the frequency. Now, the frequency of the system is constant, it's just different to what it was when it was truly free. So it's slightly reduced on truly free, but then as the amplitude changes each cycle, that doesn't affect the frequency. So it's not like the frequency changes throughout the damping. It's a constant frequency. It's just slightly less than the natural frequency. Have seen exam questions where they've wanted you to say, come up in multiple choice, that the frequency is unaffected by damping. So very light damping will have a very negligible effect on this. It's more correct to say, but the heavier the damping, the greater that is. Now, point on light and heavy damping while we're talking about that. Light damping essentially means that the amplitude will reduce only a small amount each cycle, and heavy damping means it reduces much quicker throughout the cycle. And it's actually a coefficient for that you can use mathematically to describe that's beyond the A-level course. But the key thing is they are relative terms. Light and heavy can be applied to all types of damping, and they're relative terms. So we'll come to that when we look at the other types of damping where the confusion sometimes arises. Okay, now critical damping. Critical damping is a scenario where the system returns to equilibrium in the shortest possible time. So if you imagine you displace it from equilibrium to amplitude and you release it, essentially it stops back at equilibrium. So we've got a damping force in place that something should follow simple harmonic motion, but the damping is such that it completely cancels it out, returns it to equilibrium, and it stops there. That's perfect critical damping when it does that. And you can imagine that like a slamming door almost. It's at an amplitude, you shut it, but it slams shut, and the damping force there is the catch getting hold of the door and stopping it moving. So it stops it dead. Now, that is a very specialized case for that happening. It does happen, and it happens, as we said there, in just a quarter of a cycle from amplitude to equilibrium and stop. Sometimes, as in the diagram at the bottom, there's a partial overshoot, so where it reaches equilibrium, can't completely stop, but is dragged back pretty quickly. That's sometimes lumped in with critical damping. Technically, it's not. Technically, it's just below critical damping. It's just ever so slightly underdamped, but it's pretty close. So you might sometimes see critically damped systems like the one in the bottom that follow the shape of a simple harmonic motion oscillation to start with, reach equilibrium, and then just go through a tiny little cycle to get them to equilibrium. The top graph, incidentally, you'll see doesn't follow the normal pattern first. It is a curve essentially the other way. That's assuming that your damping force is applied throughout the whole cycle there. So it's being brought to equilibrium. It's not getting to equilibrium and suddenly stopping. And then there's the concept of overdamping. So we've had underdamping, critical damping, and now we're looking at overdamping. And overdamping is where the system returns to equilibrium very slowly. So there's some force applied that means it doesn't follow its normal quarter of a cycle to get to equilibrium. It takes much longer than a cycle, so there's no oscillations at all with overdamping. So it's something, if you can imagine, perhaps if you considered the pendulum and you, instead of releasing it just through air, did it inside a really thick oil, for example, then that pendulum would just slowly be dragged back by the oil, wouldn't get through it very easily, and would be brought to rest at equilibrium eventually. But that would take much longer than the natural frequency. So it's a very long cycle. Again, it's an exponential decay. The decay of that displacement is exponential. So overdamping, no oscillations, and it takes much longer than a cycle to return to equilibrium. And you can imagine there's uses for all of these different types of damping. There will be times where you will want to critically damp something where you don't want it to oscillate at all. There are times where you want to overdamp it to again, to stop it oscillating, but not to stop it quite so suddenly, because that might cause damage. For example, if you think about the examples of slamming doors and things, well, if you slam a door, it makes a huge noise. But now, if you think about kitchens, they have these, quite often they have these drawers that close very slowly. So you give them a push, there's damp in there to slow it down. They've been over damped, so they don't slam and they don't cause any damage. There's times where critical damping and over damping are a problem. So, for example, in a car suspension, there's a valuable sort of bit to look at in terms of damping. If you don't damp it enough, then the car, when it goes over a bump, will just continue to bounce. So you need heavier damping than that. But if you overdamp it too much, it won't return to equilibrium, and it can give you, and if it's too close to critical damping, it can be quite a sharp jerk to equilibrium, which would be an uncomfortable ride. So it's getting that balance correct for each different context that we're looking at. Now, just to go over this point again, because it's really important, underdamping, it continues to oscillate, amplitude reduces slowly over time. Critical damping, it comes to equilibrium as quickly as possible, and overdamping, it returns to equilibrium without oscillating, but over a long period of time, longer than a time period. The terms light and heavy are sometimes used incorrectly for underdamping and overdamping. Sometimes overdamping is called heavy damping and underdamping is called light damping, which is technically incorrect. It's correct in that overdamping is heavier than light damping, but heavy and light are relative terms. You can have heavy and light underdamping. You can have heavier and light overdamping. So just bear that in mind. If it's heavier overdamping, it will take longer to return to equilibrium than light overdamping. So heavy and light describe the speed, if you like, at which these things return to equilibrium. But the term for these crossover points is under, critical, and over, and they're the ones that you need to know. This graph just sort of illustrates that, and I mentioned the coefficients earlier, so without going into a huge amount of detail on it, but just to give you an idea. So with the coefficient being 0, it's free vibration, pure simple harmonic motion. That's the black line on the graph. As that coefficient increases, you can see through the green, then the blue, then the red, that we are underdamping, but we are reducing in amplitude each cycle. So heavier damping. As we get to 1, that's the purple line, that's the critical damping scenario, and then with the coefficient above 1, that gives us our our overdamped scenario. Okay, looking at forces, force vibrations from a different context now. So we've looked at taking energy out of the system using forces. What if we are putting energy into the system using forces? So this is looking at forced vibrations. So forced vibrations, as it says, are a result of a periodic repeating force acting on the system. So the key thing here is that the force is periodic. So the example, which is frequently used, pardon the pun, is a child on a swing. So there's the animation. So if we just let the child swing on the swing, eventually damping would reduce the child's amplitude and she'd come to rest on the swing. So to prevent that happening, there's a periodic force, in this case the man pushing the swing. Okay, and he's doing this once per cycle as it happens. Now that's an important feature that we'll look at in a second, this one swing per cycle. But that's stopping her returning to equilibrium and is maintaining some energy going into the system to keep the oscillations going. But it's a periodic force, it's not a constant one. The system then vibrates at the frequency of the force instead of the natural frequency. So less easy to think about in the context of the swing, but is something we'll look at in a little bit. And that force, therefore, either transfers energy to or from the system. So it can act, as in the case of the swing, to put energy in, but it can also act to damp it. So if we look at a frequency response curve, what actually happens at different values here. Okay, so the frequency response curve essentially tells us how the system responds depending on how the driving force frequency compares to the natural frequency of the system. And at high or low frequencies, there's quite a limited response. So essentially, if we go back to the child on a swing example, if you push the child only every 3 or 4 cycles, so at a lower frequency, then the motion will be allowed to damp out between, and you won't get much response. You only get a slight increase in amplitude. But if you do it more and more frequently, up to 3 pushes, a push every 3 cycles or a push every 2 cycles, or in the prime example, a push every cycle, you will get a bigger and bigger response from that clearly. Similarly, on the other side, if the frequency of the push is actually higher than the natural frequency, then at some cases you'll be pushing in the same direction as the motion, so you'll be increasing the amplitude, but there will also therefore be points where you'll be pushing acting against the motion, so that then would take energy out of the system. So again, the frequency response or the amplitude is reduced at high frequencies, and the graph illustrates that the high frequency response occurs when the driving frequency is aligned with the natural frequency. As the frequency approaches the natural frequency, the response is greater. So if the child has a natural frequency on the swing and you push at that natural frequency, what you will get is a maximum response, because you are inputting energy at the right point in every cycle to push further on. Which means you're just transferring the maximum amount of energy to the system. Now, theoretically, if there's no damping in the system, actually, if you push at the natural frequency, you get an infinite response. So this is another reason why damping is important, because actually that is nothing short of frightening for a child on a swing, there's other places where this will become quite a dangerous scenario as well, where damping is necessary. We'll talk about that in a little bit. That process where you drive a system at its natural frequency is called resonance. So that's a key word to take from this. Resonance is driving a system at its natural frequency. If the system is driven at a frequency other than its natural frequency, it doesn't oscillate at its natural frequency, it does oscillate at the driving frequency. And that's an important thing to remember. But that means you'll get a diminished response. Might be still get a higher amplitude than if you just let it go freely, but you will get a diminished response. So resonance, when it's driven at or close to its natural frequency, that's when you will get the maximum response. So, as I said, with no damping on the graph, that's the dotted line. That gives us technically an infinite response there, which has huge implications. So the lighter the damping, then the bigger the response. And also you'll see from that very high amplitudes can be achieved at resonance, but there's some damping will take out of the system. But as damping increases, that response curve gets flatter. And the key thing is that the peak amplitude shifts to lower natural frequencies. There's actually just a shift on that line from the left where the maximum response actually occurs. Bigger amplitude, and that's where it's the biggest amplitude, and that's because, as we said, the natural frequency of the system actually slightly reduces with damping as well. Okay, so one application of resonance that is really just used to demonstrate the effect is something called Barton's pendulum. So there's a little diagram set up here. There's also a separate video clip which demonstrates a real one for you that is worth a look as well. So I'm just going to go through it briefly here. So what we've got is a driver pendulum, which is X on the diagram, which is the heaviest pendulum in the system. attached to a string across the top, and you set the driver pendulum in motion, and it oscillates with simple harmonic motion at its own natural frequency. That then drives the frequency of oscillations across the string at the top, which forces the 5 lighter pendulum to vibrate at or oscillate at the frequency of the driver pendulum. So they are at a driven frequency. The key thing there with them being lighter is that if they were heavier as well, then their motion would then feed back and affect the driver. So with the driver being much heavier, its inertia then dominates the system. So the greater the mass of the driver, the more effective this will look and less complicated essentially. So the string across the top that oscillates forces the others to oscillate with the same frequency as the driver. So they're not oscillating at their own natural frequency, except for pendulum C, which if you look at that is the same length as the driver pendulum, so has the same natural frequency. So the driving frequency equals the natural frequency of pendulum C, which means that resonates, and you get the greatest amplitude response from pendulum C. However, what it does do is lag the driver by 1/4 of a cycle, or pi/2 radians. The maths behind that is degree level maths, so for now just take it as a qualitative approach. The shorter pendulums, D and E, they have reduced amplitude oscillations. E will have the smallest, being most different from the driver, but shorter pendulums actually oscillate in phase with the driver, and the longer pendulums, A and B, they actually again will have reduced response, so smaller amplitude, but they now have a lag of a whole half a cycle, so they are pi radians out of phase. So the key thing here is to just learn the phase relationships. They're just something you have to know. So shorter pendulums in phase, the resonating pendulum is pi/2 or 1/4 of a cycle out phase, and the longer pendulums are approximately a whole half a cycle or pi radians out of phase. So some uses of resonance. Okay, so musical instruments, they make use of the idea of resonance. You cause a vibration, so in the case of the guitar there, you pluck the guitar string, and that vibration matches the natural frequency of the air in the guitar chamber, and that makes the air vibrate with a resonance essentially, so a maximum response to amplify the sound as much as possible. And most musical instruments work off a similar principle, where the driving frequency matches the resonant frequency of an air chamber quite often, in order to make a maximum response and get the largest sound out. Radio and TV signals, and in fact there's an awful lot of resonance in any AC circuit, but essentially the dimensions of an aerial can be changed to tuned essentially. It's usually done internally within the system, but you actually change the dimensions of the conductor to match the frequency of the radio station. So the radio station or the TV station you're looking to broadcast, the frequency that's broadcasting at, you change your aerial so that its resonant frequency matches that, which means it will pick up that radio station and not others, because it responds best to that radio station. Microwave ovens work off the idea that they're set so that the frequency of the microwaves matches the natural frequency of water particles, so that water particles absorb the most energy and therefore absorb the microwaves and heat the food. Lasers use the natural frequency of the excited atoms to generate a laser beam of a coherent source, so it will emit a frequency based on that. MRI scanners, similar to, they're not similar to microwaves at all, but similar sort of idea, where the electromagnetic field that is oscillating is designed to do so at the resonant frequency of hydrogen atoms, or the natural frequency of hydrogen atoms, to get maximum excitation from those, so that when they de-excite, they relax and produce a signal that can be detected. And ultrasonic cleaners. So again, the ultrasound is designed to match the natural frequency of the fluids within them to cause maximum vibration to ensure that the bubbles formed are able to do the cleaning processes. And there's lots of other uses of resonance in that sort of respect. But it can be a dangerous process. So where sometimes we actually want maximum response, sometimes maximum response can cause us a few problems. So if you think about machinery, so any machinery with a motor, that motor will have a frequency. If that matches the natural frequency of the machinery, it will make the machinery vibrate. So the motor's the driving frequency can make the rest of the machinery vibrate quite violently, which can cause problems, can actually break machinery apart. So usually machinery will be damped to make sure that the motor frequency does not match the natural frequency of the machine itself, to make sure that effect doesn't happen. Classic one. If you were to sing at the natural frequency of glass, it is possible to shatter the glass. So it depends on the dimensions of the glass in question, whether it's a window or a drinking glass, and all sorts of different things. So each glass will have a different natural frequency, but if you can produce a sound wave that matches that natural frequency, you can make the glass vibrate with increasing amplitude and causing it to shatter. Feedback is an example of this, and it's pretty clear why they would match. If you've got a microphone too close to the speakers, then the microphone will pick up the speakers, and clearly they're being set to work at the same frequency. So that's an example of the feedback, with the speakers picking up, with the microphone picking up its own signal coming back. Biological resonance can cause a bit of a problem. It links a little bit to the machinery one. If this is something that has been recorded with people who work with heavy plant machinery quite a lot, where if the machinery is operating at a frequency that matches the natural frequency of, say, a body chamber, so the abdominal chamber, it can cause a great deal of discomfort as the internal organs essentially and the air within them, or the fluids within them, vibrate with increasing and it can cause some quite severe conditions and illnesses as a result of that. And obviously there's some hearing issues that would be related to that. So there's some phenomena there that need to be considered. Wolf notes, actually not to do with the wolf themselves, but this is something you will have picked up and heard at various points, where there might just be a wind, for example, that blows across and makes a window vibrate in a certain way, just because it matches the natural frequency of the window, and it can sort of make a sort of essentially a howling noise. You might have heard it across bottles, empty bottles, when air blows across an empty bottle. That can produce a wolf note, which can be just an unwanted disturbance. You can also get them with certain musical instruments. If musical instruments aren't designed well enough, essentially, there will be a certain response at certain frequencies that ends up being much louder than at others, which can then dominate a musical piece. So that's the idea behind wolf notes. And then probably the most famous is concepts with civil engineering. There's examples throughout history of large buildings falling foul of resonance issues. Essentially, the most obvious one to consider would be any city that is built near an earthquake, and if an earthquake occurs at a certain frequency and a skyscraper or a bridge has the same natural frequency, then the amplitude of vibration will be much higher and can cause a great deal more damage. So buildings, suspension bridges and things need to be damped so that those situations don't occur. And it can be as simple as there's been issues in wartime with armies marching across bridges. If the frequency of the army's footstep matches the natural frequency of the bridge, it can make the bridge vibrate and sway quite a lot. So armies quite often are asked to break step and not march in formation as they cross bridges, things like that. Famous example with the Millennium Bridge when that was built in London across the Thames, people's footsteps sort of seemed to match the natural frequency of that and did cause it to sway quite a lot. So it needed quite a bit of damping.